Fabricademy 2019, week 5, E-Textiles class with Liza Stark. We are very happy to have you here again in Fabricademy, and I will give the word to you directly.
Cool. So, hi, my name is Liza. I'm very excited to be here. Today, we're going to go over a bunch of different facets of E-Textiles. I've been working in this space for probably close to 8 or 9 years. I teach at Parsons, the New School, among other places, and I'm based in New York. So let's just go ahead and dive in. Bear with me while I get my screen sharing together. Okay. Oops. I'm back here. So that is not, there we go. So can y'all see my, yeah? Okay, great. Cool. Okay. So let's wait for this to load. Come on, Google. Okay, great. Got a lot of images on here, so Google's working hard. All right, so here's an overview of what we'll be working on today. So we'll talk about conductive and resistive fabrics and yarns, do-it-yourself soft sensors and switches, hard to soft connections, different components that are involved in E-Textiles, and then we'll do a little bit of a dive into how to work with microcontrollers like the Arduino. So here's another sort of look at the agenda. I'll do a quick introduction. We'll look at some basic circuits. Then we'll talk about materials, different tools, connections, sensors, and programming. So before we get started, I just want to contextualize this a little bit in a bit of history and just talk about sort of why E-Textiles, why would we work with these types of materials when we have other harder materials available to us. So here are two examples from the mid 90s, late 80s, mid 90s. The first is Steve Mann, who got really into basically putting the idea of putting computation on his body and sort of augmenting his body in that way. So he started creating these wearable computers. They're very, as you can see, very bulky, very sort of invasive, and they also don't look very nice. So he was at MIT as part of the wearable computing group, and at the same time, another woman named Maggie Orth was also at MIT and saw what was happening in the wearable computing group and basically sort of reacted against it and thought, this is not sort of how we want to, or I would think about, integrating computation in my life in a holistic way onto my body. It should be something softer, more embedded. So one of the first examples that she made of what would later become the practice and field of E-Textiles was this musical jacket, where she used silver thread, embroidered it into a touchpad interface that then she could use to activate different tones. So as we're sort of thinking about the space of E-Textiles, which I'm going to define as embedding electronics into textiles that uses conductive materials like threads or fabrics to add new functionality and aesthetics to textile artifacts. This can be on the body or off the body. It can integrate crafting techniques, and it can sort of be high or low tech and a combination of both. So that sort of setting the stage in this way as we're starting to think about it, today most of the electronics that we use are embedded into are enclosed in these black boxes, in these plastic casings, or otherwise you sort of have all the circuitry, you solder it together, you wrap it up, and you try and put it in a nice case, versus actually exposing or almost liberating the electronics, using them as part of the aesthetics. So you can sort of see here 3 examples, one using paper, where you can see the traces that are embedded in the in the pulp that's been smushed and dried with LEDs. Another example, one of my favorites, the knitted radio, in which capacitors are actually knitted into this sweater using conductive thread. And then finally, one where you can sort of see the traces of the LEDs on this particular headpiece that Wei created. So as you are thinking about your own projects, and as you start to grapple with the materials, because these, I'm sure you've learned over the past few sessions with the materials that you've been working with, it's always a conversation. So as you start working with these materials and sort of grappling with their properties, you really want to consider this idea of embedding and how you can expose the materials, or when to expose and when you might need to encase for functional reasons and such. But also push yourself to see if you can really expose them. So as we're again in thinking about this combination of electronics and textiles, which usually seem to be disparate spaces, there are a whole other set of considerations that we need to be aware of and take into account. And we'll talk through those a little bit more as we go through the class. So first, we're going to start with electricity and just give a very basic overview of what a circuit is, how electricity works. We're going to take it very slow. If you have no background in any of this, that's completely fine. If you do, then it's always good to review the basics. Sometimes I still need to go back and look at Ohm's law just to get, wrap my head around the system that is, electronics and the physics of it even. Okay, so first off, what is a circuit? So a circuit is basically nothing more than a path for electricity to flow on. That's it. It uses conductive materials for electrons to move around the circuit. And so again, electricity moves through a stream of electrons. So usually, when you have one electrons, they're pretty weak. But if you have a stream of electrons, they can be very powerful. And this stream of electrons is what creates electrical current, what we call current. So now if we want to get that stream of electrons moving, then we need to create this scenario where we have greater electrical energy, a point of greater electrical energy, and a point of lower electrical energy. So it's not the perfect analogy, but you could almost think of it like gravity. Like you want to have the stream of electrons sort of slide down from one point to another. So moving from greater electrical energy or potential to lower electrical energy or potential. We could also say, instead of potential energy less or greater, we can substitute those terms for power and ground. So we can say that we want our stream of electrons to move from a positive connection or power to a negative connection or ground. Okay, so the most basic circuit that you can create has a load and a power supply. So let's say and a load is just like an actuator or something that does something, right? Like an LED. So when we have a power supply, like a 3-volt battery, and then a load like our LED, the electrons will travel from the battery up through the LED and do work on the LED. So this is one of the most ubiquitous components that you'll probably see in your work with electronics or E-Textiles for that matter. And LED stands for light emitting diode. So light and emitting, those are two words that probably are very familiar to you, but this word diode may not be as familiar to you. And diode it's a pretty simple word actually. It basically means that electricity can only flow through it in one direction. So as you're starting to look at electronics and the components that we use to build circuits, you may notice that some of them can only support one direction, electricity flowing in one direction, and some of them allow electricity to flow through them in both directions. So this means for some components it will be important how you orient them on your circuit boards or in your breadboards and your circuits. So looking at an LED, so there are many different sizes of LEDs. You can have very small LEDs called surface mount LEDs. You can have 3 millimeter, 5 millimeter, 10 millimeter LEDs. The sizes that you use, really, it just depends on what aesthetics you're going for. You can have RGB LEDs. So this means you can have RGBs that have 3 different colors associated with them. as if you actually sort of look at an LED and hold it up in front of you, you'll notice that there are two legs. So you have one leg that's quite long and that's the power. That's the leg that you attach to power. Now there's a bit shorter, and that attaches to ground. Moving up, you'll see the casing of the LED. All LEDs have a viewing angle. So sometimes you'll notice that LEDs sort of only emit light straight in front of it, or some are a little bit wider. So again, it just depends on the aesthetics that you want out of whatever project you're working. It's easy to make LEDs, these what are called through-hole LEDs. So LEDs that have the legs, non-SMD LEDs, sewable by using small pliers to wrap around the legs around and just create a small hole that's great for sewing. Lastly, it's also sort of just a quick note on voltage. So different components are rated for different voltages. So for example, most LEDs require about, somewhere between 2 to 3 volts in order to work. And we'll talk more about this in a second, which is why if you place an LED on a 3-volt battery, it works very well. It will take up all of that energy. But there are some slight variations in voltages for different colors. So for example, if you were to put a bunch of different colors on a battery and combine LEDs, you may notice that one will take more voltage than the others. So it's just something to be aware of and something that you can avoid by using a resistor. So let's talk, now that we sort of have been introduced to these concepts using this example of just a really basic circuit with an LED and a 3-volt battery, let's talk a little bit more about these abstract concepts. So voltage, again, is this electrical pressure or force between 2 points. So there's this water tower analogy that's actually quite helpful and ubiquitous when talking about Ohm's law, which is the relationship between voltage, current, and resistance. So think about a water tower. Voltage, you can say, is the height of the water in the tower. Okay, and one of the main tools that we use to measure all of these 3 concepts of voltage, resistance, and current is a multimeter. And a multimeter is very helpful. You should always have one by your side. And you can see on the right side of your screen, I've marked where you can measure voltage. Next is current. So current is the rate at which electrical charge flows. So all of that stream of electrons, if you picked one point and were to measure how quickly those were flowing, that would be current. And we measure that in amps. So this, you can imagine, is the volume of water flowing through the whole of the water tower. And you can see current on the right side of your multimeter. It's fairly rare that you probably will have to measure this, and it's a little trickier, just as a heads up. And the last is resistance. And really, this is where we'll spend a lot of our time because much of the creation of sensors and switches in E-Textiles is about manipulating resistance. So this is the amount of material that resists the flow of current. And you can, in the water tower analogy, this is the size of the hole. So the larger the hole, the more current or water will flow through it. Smaller the hole, then the smaller amount. And you will be using your multimeter quite frequently to measure ohms. Okay, so let's keep going. So again, Ohm's law, and we won't dive too deeply into this, but it basically sets up the relationship between these 3 ideas. So, if you know your resistance and you know your voltage, but you don't know your current, you can easily calculate that. SparkFun has a great tutorial on this if you're interested in learning more. There are wonderful sort of how-tos that will help you better understand this. And if you choose to do more with electronics, I highly recommend that you seek those out. So there are a few rules if you maybe don't want to dive so deeply into Ohm's law or these abstract concepts, that's fine, but just keep these sort of 3 rules in mind. So the first one is that, let me see if I can move this, electrons are quite lazy. So electrical energy will always follow the path of least resistance to ground. So this basically means we need to watch out for something called a short circuit. And short circuits can happen when you have two traces or 2 circuit paths connecting where they shouldn't. So you can sort of see in this little drawing, you have your electrons running up and doing the work to get to the LED so they can light it up and then going back down into the battery. But if we cross the stairs with another piece of conductive fabric, then the electrons are not going to go up and do the work. They're just going to take the path of least resistance. So electrons, super lazy. Rule number 2, electricity hates waste. You have to use all electrical energy in the circuit. So for example, I mentioned that an LED usually takes about 2 to 3 volts in order to light up. That's what we call its forward voltage. So if you take an LED that only needs 2 volts and you put it on a 9-volt battery, there's going to be too much voltage left over, and you'll actually burn the LED because there's nowhere for that extra, 5 to 6 volts to go. So you have to use all of it. And there are ways that you can do this. You can either add extra LEDs, you can add a component called a resistor to dissipate the heat in that energy. If you don't do that, you could damage your components. And the last rule is that circuits are a system. So you'll be introduced to many different components, and all of these components play a different role in the system, so you have to make sure that they all play nicely together. Some components, we talked about orientation with LEDs earlier. Some need to be arranged in specific ways. So you can't just sort of, stick everything in a breadboard or a circuit board and expect it all to work. They have to be situated in a specific way. Okay, so there are 2 different types of circuits that we can build. One is called a parallel circuit, and this is the one that you'll predominantly be using. And here you can see if we have LEDs, we have all of the positive legs going to one side, oriented up, and then all of the negative legs connected to the battery going down. So this is basically, a situation where all of the LEDs are sharing the same amount of voltage. So they're all getting about 3 volts of electricity, and then they're splitting the current. There's another type of circuit called a series circuit where you daisy chain ground power, ground power, ground power, and attach it to the battery that way. And in this scenario, they split the voltage. Now the problem here is that the first LED in the sequence is going to eat up all of that voltage, and the rest of the LEDs aren't going to get any of it. So it's not exactly an efficient use of our LED energy or of our power that we want to use in this particular scenario. Okay, so I'll stop briefly to ask for any questions. I know that was a lot, so if it didn't all soak in, that's okay. Anything? If not, I'll go ahead and keep going, but please, if you have a question, feel free to jump in. Okay, now we're going to move into the really fun part of this, the materials part. So let's talk about what materials you can use. So basically any that are conductive. When I teach, I teach a course called Computational Craft that I've been teaching for quite a while at Parsons, and one of my biggest learning objectives in that course is for my students to leave that course sort of putting the world into these 2 buckets of conductive and non-conductive materials. Actually, that's quite binary. I suppose it's more like the spectrum of conductive, but just sort of being able to see the world that way. So I encourage you to think about that as well. When we talk about conductive materials, there are many, out in the world, there are many conductive materials. Any that are made of metal, you would be able to use to create circuits with. Some are just better than others. But when we start talking about textiles, there are many different options that are available to you. So here is a really, really, really wonderful sort of overview that Koba Kant or Hannah Pirner-Wilson and Mika Satomi have put together about the materials that they tend to use the most. So when you are looking at conductive materials or conductive textiles and thinking about what is going to work the best for your project, there are a few properties that you want to consider and keep in mind. One is the resistance. So you want to, every electronic component and therefore all different types of conductive materials will come with what's called a data sheet. And a data sheet gives you all of the information about how how that component was made, what it's, all of the different ratings around voltage, current, etc. And it will also give you the resistance. So it's helpful to look at that data sheet and just double check the numbers. You also want to, just one more note on resistance. For example, if it's more resistive, you may want to use that to create a sensor. If it's less resistive, meaning that electrons can get through it very quickly. So copper, for example, has a very, very low resistance, and that's why we use it in PCBs, because it allows the electrons to get from point A to point B very quickly. So it's a very efficient material to use in creating electronic circuits. Next is stretchiness. So depending on what sort of project you're making, if you are making something on the body that maybe needs to be used at different joints, or if it's something that doesn't necessarily need to go on the body and that doesn't need to touch skin, perhaps you use different types of materials for those. Perhaps you use a polyester taffeta on something that doesn't go on the body, and a silver stretch conductive fabric that goes on the body. Solderability, so some of these materials you can solder to. Soldering is basically using a very pen-like implement that gets very, very hot, and you glue with metal. Some of these materials you can solder onto, which is very helpful, but you should always test beforehand. Feel is another really important thing that you want to take into consideration. And then also the substrate and the productive process. So what's the sort of underlying textile material? Is it nylon? Is it polyester? And how is that going to impact the project that you're working on? And if you're trying to approach it in a more sustainable way, which can be, a challenge with E-Textiles, you want to consider that substrate as well. Okay. So that was fabrics. So now we're going to move into threads. Again, there are other properties that you want to consider, similar properties to consider with these materials as well. Resistance, solderability, but you also want to think about thickness, so what the ply is. Thickness usually is related to if it frays easily, some of these do tend to fray, and if you have fraying, that can lead to the possibility of more short circuits. Remember, we talked about electricity is lazy, so we don't want that to happen. And if you can put it in a machine. So you can put many conductive threads, in a sewing machine. It just has to be in the bottom bobbin. And then you also want to know about the substrate. So is it stainless steel, or is it silver? Is it coated nylon with silver? All of these will impact the way that it interacts with the textile in the productive process and how it ages overall. So a few examples you can see here. The one that I really love to use is the Carl Grimm conductive thread. It is solderable. It comes in a coated silver and also in a copper, and it's just quite durable, and the resistance is very low. Some, like the Bekanox, are much better used for heating circuits. So if you are using thermochromic inks, which we'll talk about in the next section, the next class, you're going to want to use stainless steel because it has a higher resistance, which means that you can get it to emit more heat. So it's better for that. So there are many materials to choose from here. You should always be on the lookout for new threads or fabrics or yarns for that matter. Tapes and inks. We won't so much go into these, but you should be aware that they exist. There is the Q-Pro Coat by Less EMF. This is made of copper and it's water-based. It can be very conductive. It's a good option for silk screening, though you will need to add some additional materials to it to make sure it doesn't clog up your screen. Bare conductive, some of you may have heard of, is good, but it's quite resistive, so it's better for making like touch sensors. And then Circuit Scribe is another product that you can use that's very, very conductive. It's good for writing or drawing. Copper tape is one of the best materials that you can use to prototype with. Often when you build a circuit, when you're making a project with E-Textiles, you'll want to start by building a circuit on a breadboard, which we'll get to in one moment. and just making sure that all of your components fit together correctly and your circuit works. Then ideally you want to build that out using copper tape and sort of redraw or reconfigure your traces in a more aesthetic way if that's what you're going for. And then if you decide to move on to fabric or to threads, recreate that circuit. So copper tape is just like a really easy way to prototype. There's also copper foil sheets and then conductive fabric tape. So now that we've gone through our materials, I want to talk through tools. So let's see what's available to us. So you can use tools with your hand like, pliers. Small jewelry pliers are really helpful to always have on hand. Belting needles, I highly recommend if you want to do a lot of work with conductive thread, getting a little bit of beeswax. It helps when you're threading the needle if you're embroidering or hand sewing. You'll want to have a nice pair of, if you hold your scissors dear to you, you might want to get another cheaper pair to cut conductive fabric with because it will eventually dull your scissors. Don't use your nice fabric scissors on conductive fabrics. Straight pins, a snap press. If you have one of these available to you, that's a great tool to have around to make connections. Embroidery hoops, embroidery needles, tailor's chalk, and then depending on sort of what you specialize in, and if you have knitting needles, crochet hooks, all of these can be very helpful as you start to work in this world. In terms of machines, just some that, if you have access to them, amazing. A laser cutter can be very helpful. If you don't necessarily have access to that, you can also look at using a vinyl cutter. There are lots of fairly cheap vinyl cutters on the market today, like this Cameo by Silhouette that does a really nice job cutting conductive fabric. Embroidery machines, also wonderful to use. You should always test, you're going to want to test if you want to use conductive thread in these machines, test it before you actually start working on your project. Some weights and plies of conductive thread are better than others here. And then sewing machines. So again, if you want to sew with conductive thread, remember to put it in the bottom bobbin. Otherwise, you'll have a whole big mess if you put it in the top. And then it's always helpful to have an iron on hand. One way that you can attach conductive fabric to a textile is by using iron-on fusible interfacing. So this is always helpful here. But a quick note of caution, if you're using a conductive fabric that has a substrate of polyester, you just want to be careful to use it at the right setting. Otherwise, you may end up in a scenario where you heat up the conductive fabric too much, and then it actually causes the resistance to increase because you've then melted the conductive material into polyester, and it's all a big mess. So just remember to use the correct setting. Okay, and then tools for electronics, working with electronics. Your multimeter, this is a tool that can help you measure current, voltage, and resistance. So you'll always want to have, and just connectivity in general, so you'll always want to have this on hand. A soldering iron, which will help you, which will allow you to connect, to create a permanent connection between a component, between two components, or between a component and solderable fabric or thread. And finally, alligator clips, which basically you can use to create temporary connections between components just to test if something is working in your circuit or not working in your circuit. Okay, so I'll stop again. Any questions before we move on to hard and soft connections?
Yeah, there is a question before from the previous
Yeah,
question.
actually, so I should have asked this question when you stopped before, but
yeah, go ahead.
When you have a series circuit, what if the battery has a stronger power than the first LED could take? Would it be better to use other ones after it?
So if you have like a 9-volt battery and you have 3 LEDs, and those LEDs, as I said, take up let's say 3 volts, you can put those 3 LEDs in series and they will all light up. because you're giving them the same amount of voltage on the LED side as the battery. Does that make sense? So you have three LED, 3 times 3 equals 9, so you have 9 volts and 9 volts, so they'll all light up.
And so what if, what if when is it useful, the series circuits, other than these times at which it adds up like that? Is there another appliance to it?
Yeah, so series circuits are useful when you're using like resistors, for example, or different types of components, because they have additive or subtractive effects. There'll be a scenario actually a little bit later in this presentation where you'll see 2 resistors in series. So a resistor is a component that you use to limit the amount of current. And if you have 2 of those in series and then you can divide them, you'll be able to basically sort of, with an Arduino, turn a change in voltage into, or a change in resistance into a change in voltage that will allow the Arduino to read like a sensor that you make out of resistive yarn, for example. Long story short, these components or series circuits are helpful not so much with LEDs, but with other components. Cool.
Nice, thank you.
Yeah. All right, I'm going to keep going. Cool. Can everybody see my screen? Good. All right. Okay. So now we're gonna talk about options for. Hold on one second. Hey, Alex. We're gonna talk about options for creating traces. So a trace is basically when you're talking about creating circuits. We have lines of conductive material that we use to connect our components and our power sources. And so as we're thinking about creating these traces, these conductive lines, we have lots of different options. So on the left side, you'll see that that's basically like your standard PCB. On your right side, you'll see that there is a circuit that's made of conductive fabric, and the traces are connected via conductive yarn and probably a little bit of soldering on that circuit. Sorry, hold on one second. So as you're thinking about creating circuits, you can see, circuits that are designed for PCBs are designed for efficiency. That's why they have sort of the aesthetics that they do. But when we're thinking about designing with conductive fabrics, we don't necessarily need to have that same sort of efficiency. We can really focus more on the aesthetics because we have more leeway. So when we're creating traces with conductive fabric, you can do sort of your basic straight traces. So here we can attach those using, moving from, in examples A through D, we use an iron with adhesive fusible interfacing. So this is a great way to really just easily lay down a trace onto your fabric, especially if they're a little bit more intricate. You can use a very small iron to be able to get them down. You can also hand sew, obviously, or machine stitch your traces if they're a little bit thicker. It all just depends on what works best for your project. And I highly recommend that you create sort of different samples as you're working with these materials just to understand their properties a bit better. Right, I did have a slide on this. So in order to work with this fusible interfacing, like heat and bond, for example, here's a slide that will sort of walk you through the process of doing that you can go back to. And again, it's a very, very easy, simple way to just lay your traces down on a textile. Just make sure you have it at the right setting for both your conductive fabric and the substrate that you're laying or that you're fusing it onto. Just a few examples of fabric traces in the wild. So this is Second Skin by Rachel Frere. So you can see her traces that she's put on, or that she's laid down here using fusible interfacing. And she has also on the right side, she's put a netting on top of it in order to insulate or cover those traces so they won't be, it won't create a short circuit or be disturbed otherwise by other materials or the body. Here you can see another piece by Aphrodite Pissarra. So she has created these fractal antennas using a vinyl cutter, I believe, these really, really intricate patterns with the copper taffeta fabric, and then she's ironed them on. Really, really beautiful work. Thread, so the way to lay down traces here, you can either machine stitch them, you can embroider them, you can hand embroider them or machine embroider them. You can do a zigzag stitch over them, so maybe if the thread is too thick to go in the machine, you can just zigzag over it as in C and D, or you can always just easily hand sew it. Again, it just depends on the project and the material that you're working with. So here you can see some really, really beautifully hand embroidered traces by Koba Kant in The Crying Dress. And also equally impressive hand embroidery done by Irene Pash and Ibu Korbak in their embroidered computer. So as you can see, they've just created all of these different interwoven traces out of a variety of thread and gold thread and bullion. Tapes and inks. So there are, if you decide to work with these materials, you can screen print them, you can cut them on the vinyl cutter. There are lots of different opportunities here as well. So now we're going to move into one of the sort of areas of E-Textiles that tends to be the most challenging, but also the most fun. In terms of experimentation, so this idea of making hard and soft connections, because you're working with these hard components and boards, and then you also have these soft materials that you want to connect to. And one of the most important things to always keep in mind is that you must have a secure connection between any components that you're working with in order for electricity to flow properly between them, so the electrons can get from point A to point B. So here are a few examples of hard to soft connections. So you can sort of create these breakouts, as in the snap breakout by Koba Kant. They use a snap press and poppers. You can also see using what are called header pins, that are pretty pervasively used in physical computing and electronics in the multi-stranded wire. So they basically have conductive thread that they have then shielded using beads, and then they've soldered that thread to these header pins. And then a few experimentations used in the bottom two examples from E-Textile Summer Camp as well, using all sorts of conductive materials that you use every day but may not really think of in this as this type of tool, like a safety pin, for example. So here are a few different examples of how you can connect components. So you can either create permanent connections or temporary connections. Here is examples of permanent connections for LEDs. On the left side, you just have hand-sewn and embroidered connections with conductive thread. And on the other side is LEDs that have been soldered to different conductive traces. And it's important that if you do solder onto conductive thread or conductive fabric, you want to be sure to cover those what we call joints with hot glue or fabric glue, just to make sure they're extra secure. If you want to work with really, really super tiny LEDs, you do the same thing. It's just a little bit more involved, and tweezers can be quite helpful. And then, always definitely want to cover those joints with fabric or hot glue to make sure that the components stick down. If you want to, let's say you have a circuit board that you want to connect to thread or fabric, Here is an example, several examples actually, of ways to do that. You can either sew into the circuit board. If you have a fabric trace that you've laid down, you can sew into the board and then onto that. You can also just use wire and sort of create a sewable hole as we saw with the LED. There are lots of different options. So if we want to create a non-permanent connection, so there are many options for that as well. Snaps are really a great option here, as you can just snap them on and off, as in example A and B. So you can either hand sew them or you can use a snap press. Example C is a silicone wire with a safety pin. That's also easy to undo, and maybe a little bit more dirty when it comes to testing and prototyping certain projects. And then example D is just a clip with paracord and then conductive thread inside of it, so it's all connected together, and some conductive tape. And these are really nice tools to have around, especially if you are, for example, working with a fabric like silk and you want to create connections, but you don't want to damage the textile or the garment that you're working on using pins, you can, or alligator clips, because those little teeth can create holes on really fine textiles. Then you can create tools like this to help prototype your work. And I have given Nat a series of links that will allow you to go check out various tools that other folks have created that have tutorials with them. So one of the things that you're absolutely going to encounter if you do work in this space is when you're creating your circuits, you're going to eventually have two traces that intersect that you do not want them to touch at all. So there are different ways of what we call isolating traces. So making sure if you have two traces that intersect, that they don't actually touch. So for example, you can use fabric to create a layer in between them. You can use a piece of paracord, you can use beads, you can use tape, or you can, if you're working with thread, you can sort of go under one of the traces. So lots of different ways to approach this. You want to be as clean and neat as possible within this space, because again, we really want to watch out for short circuits. So you can see the image on the left is something that's in process, and all of those conductive threads, if that was hooked up to a circuit, would just short out everywhere. It'd get really hot and it'd be a big mess. So you want to make sure that you secure all loose threads, that as you're connecting to different components, you're creating that strong connection, and to glue down anything that looks like it might fray or accidentally touch another trace that you don't want it to. Okay, so we'll stop here once more for any questions before we go into sensors and programming.
Hello.
We have a question.
Hi. Yes.
Hey. I got a question. In the case you wanna wash the clothing and everything, it's gonna, I don't know, deteriorate with the wearing and washing.
So how to wash it, or what will washing do to the materials?
How to prevent that it's gonna be damaged with the washing, or to disconnect something to wash it apart, or I don't know.
Yeah. So when you wash any of these, so if it is something on the body or something that may need to be washed, you're going to always want to take out any boards. So if you have an Arduino board or a LilyPad board or a Teensy or whatever, you want to make sure that that board can be removed before you put it in water, ideally. Next, before you even start in on your project, you should assess whether or not it will need to be washed, and then you want to choose your materials accordingly. What materials might deteriorate faster with a washing process, and which might be better for that. You never want to machine wash anything, because it's way too much sort of manipulation and could cause things to pull apart. So you want to just gently hand wash it, and then make sure everything is completely dry before you put any power to it. Does that answer your question? Okay.
There is another question. If these are isolated, or if we touch with our hands, they will make short circuit, and if the width is varying the conductivity.
What was the second question? One more time.
If the width of the trace.
Great question. I'm going to address the second question in the next section. So if that doesn't get answered, please bring it up again when we stop for questions. But for the first question, so our bodies are made of water mostly, which water is conductive. But that being said, the resistance of our skin is quite high. So even if we touch circuits, it won't create any, even though like our skin is mildly conductive, it's not enough to create any sort of short circuit if you touch between two traces. That being said, if you can, there are scenarios and circuits and code that you can use to create a situation where if you touch a trace, it can cause an interaction that would trigger an LED or some other sort of output. But that's not something that you need to worry about for short circuits. Cool. Any other questions? All right, we'll keep moving. Okay, so now let's get to the really fun part. We've covered materials, we've covered how to sort of build with those materials, and now we're going to talk about sensors, so how to take those materials and craft them into objects and components that can actually read information, take data in from the world. This is the fun part. So sensors and switches are forms of input, and when we talk about input, we can talk about digital input and we can talk about analog input. So when we say the word digital in this scenario, what we really mean is an on or off state, this binary state, where you have an on state or a 1 state or a 0 state, off state. So the other form of input that we can discuss is analog. So this is when we talk about sensors, we refer to them as analog. They give us a range of values. Specifically when we're working with a microcontroller like Arduino, we get a range from 0 to 1023. So these are sort of two different ways that you can categorize input. So first we're going to talk about switches. So this is the digital, so either on or off. The switches have two states. And when we talk about switches, switches are nothing more than a break in a circuit. So you create this path for electricity to flow on, and then at one point in that path, you break it. And then if you want to be able to close that again, you create a scenario where you're able to actually recreate the circuit where you're able to close it again so electricity can flow. So there are many different types of switches, but we'll go through a few of those and how to make them. Again, there are links with tutorials on how to make all of these from my own site as well as Kobakon's sites, a bunch of different places. So the first is a momentary switch, and these are like push buttons. So as long as you hold them down, the switch will stay closed. Because basically you have two conductive materials that have a barrier between them, and when you press them down, it will allow those two materials to come into contact and electrons will flow, as you can see here. So next is a toggle switch. So this is basically, unlike a momentary switch, when you close this switch, it will stay closed. You don't have to continue pressing it down. So again, as you're thinking about the projects you want to make and how you want people to interact with your circuits, this is something you need to consider. If people always need to be pressing, or if they can just sort of close a snap and that will be it. That's how you turn something on or off, or close a zipper. So here you can see different ways or examples of how you could potentially make a toggle switch. And there is, on these slides, you'll notice there is a circuit diagram at the bottom. Once we get through the Arduino portion of this presentation, those will probably make a lot more sense and you can use those in reference later on. Oh, right, here's the zipper one. Next are tilt switches. So this is one of my favorites. It's sort of a design that Hannah Perner Wilson came up with many years ago, and you can get really really expressive with sort of how you build this. And this is basically you can use a conductive bead or pom-pom, and it'll make contact with these fabric patches based on the positioning of the swatch. Or of whatever garment or piece you're working on. And so as you can see, if, for example, it's oriented down and to the right, it will activate that patch or the LED that's connected to that patch because it'll complete that circuit. So it's sort of like you can connect in this scenario, 4 different mini circuits. Next is the stroke switch, or sometimes called stroke sensor, even though it really is a binary state. So in this scenario, you have two sort of channels of conductive yarn or conductive thread that when you sort of do a stroking action, you allow those 2 channels to touch each other, and that will trigger an output. So here's an example of how that works. So again, at rest, these 2 channels are not touching, and as you stroke them, those 2 channels do touch, which will allow you to read data into a microcontroller, or will allow the circuit to complete and trigger an output. Okay, so that was just a brief overview of different switches. Remember, switches are sort of have these 2 states, binary, on and off, and now we're going to move into sensors, which will allow you for a much broader range of input. So for example, a lot of sensors can be created, and you'll see a lot of similarities between the construction of switches and sensors here, because basically you're still creating a break in your circuit, and now you're just adding another layer of material that is resistive, and that when we either press on it or stretch it, allows us to manipulate that resistance to get a varying resistance, which is why you may also hear the term variable interchangeable with these types of sensors. Variable resistors interchangeable with these types of sensors. So again, as we deform or manipulate these sensors, we can change the amount of current that's getting through the circuit, which will change how bright an LED gets, the frequency of a sound, or the speed of a motor. So we usually there are a couple of materials that are highly specialized to creating sensors. When we're talking about fabric sensors, there are 2 in particular. One is called Velostat. It's a bit of a plasticky material. It's really, really great. It's quite cheap, actually. And it's used for creating pressure sensors. So it's basically a bunch of different carbon fibers that have sort of a nano space in between different layers. And so one layer is all sort of oriented this way, and the other layer is oriented this way. And as you press down, those layers come into contact and allow more electrons to move through. The second fabric is E-Tex. So E-Tex is a really, really incredible sort of material that unfortunately in the last year or so has not become so easy to obtain. It's made by a company out of California that basically uses a proprietary coating process that will allow you to infuse basically any textile material with a very specific amount of resistance. And I believe maybe y'all have access to some of this. But if you do, please use it, please test it. It's really, really great because not only does it decrease the resistance across distance, but also pressure. So it's great for making stretch sensors, for example. So next, and sort of in response to the second question from the last round, there are 3 different ways that we can manipulate resistance, that we can change resistance. And we use all of these different ways. I guess I should say, as you're looking at these sensors that we're about to go through, you can sort of check off in your mind how they're using these ways of changing resistance in order to get sort of the behavior that we want. So the first way we can change resistance is distance. So no matter how conductive a material is, the resistance will always increase, meaning it'll be harder for electrons to get through a particular material over distance. That's why you have these, cables that go under the ocean. They're incredibly thick in diameter because you need more area because for the electrons to flow, because there's such a wide distance between continents, right? Usually this doesn't matter over, they're like under a foot for many conductive threads, but if you're talking about, creating a much larger piece that spans feet or meters, then you're going to have to account for that. Next is contact. So we can change resistance by how much sort of pressure or contact we have two materials making. And then the next is surface area, which is related to, all three of these things are related. But basically, increasing the size of the area for electricity to flow will decrease the resistance. So for example, if you have one piece of conductive thread that you stretch out that's, 3 meters long, the resistance will be higher than if you embroidered that same 3-meter length of thread into a satin stitch. So it created a little bit more surface area, but less distance. Okay, so the first pressure sensor, or the first sensor that we want to talk through is pressure. And this is like a fairly simple sort of like hello world of pressure sensors. You have 2 pieces of conductive material and then velostat sandwiched in between them. So the 2 sides of conductive material are not touching at all. They can only touch through that velostat. And then as you press down, you allow more electrons to flow through them, and you can read those in a circuit or using a microcontroller. So here's more of a diagram of how to create that. And in this situation, generally, as you're creating pressure sensors, it's you get higher sensitivity, or sorry, you get increased sensitivity the more surface area that the velostat is touching. So if you create a pressure sensor with 2 pieces of conductive fabric, it will be extremely sensitive. And basically the LED that you're connecting it to, for example, might always be on. But if you're using conductive thread, just lines of conductive thread, it won't be as sensitive, and you'll get more of a range as you're pressing down on the velostat. You can also create pressure sensors out of E-Textiles, where you basically have 2 pieces of conductive fabric that are connected through a piece of velostat, and when you press down on it, you'll be able to read that change in resistance. So next is a bend sensor. You may notice the image on the right. It looks very similar to a pressure sensor because it is. It's basically a pressure sensor just in a different form that will allow you to, for example, put it on a joint and it'll get more, the resistance will change at the point of bending. So here is an example, the diagram example. Next is a potentiometer. So here, potentiometers are basically, if you think about knobs that you use on, I want to say CD players always, but that's super outdated, I guess, at this point, but like a knob on like an audio player or even, some other sort of audio board that you can change volume on, for example. So this is where you adjust the resistance by connecting the conductive material and the resistive material through a wiper. So as you move the wiper around the circuit, you'll be able to decrease or increase the resistance, basically changing, for example, the brightness of an LED. The further away you move, the more resistance you'll have in your circuit. So you can see here, I'll just move this over. as you start the wiper where the resistance is having access to that resistive and conductive material. Here is sort of a version of an analog tilt sensor where instead of having the conductive thread connected directly to those patches, you actually have a little bit of Velostat or a little bit of E-Tex connecting through the conductive thread and the conductive fabric. Next is a stretch sensor. So this stretch sensors, you can use conductive yarn. It's a really great way to build an easy stretch sensor. And you usually get a lot of range out of them. They're really great. And basically, as you stretch these sensors, the resistance decreases, allowing more electrons to flow because you have the conductive sort of materials at a basic level getting scrunched together, so you create more surface area for them to go through. So at the top are two different knitted versions, and then at the bottom is one with the E-Tex. So here you can see an example of how to create one with the E-Tex. It's very, very simple. It's worth noting here that E-Tex generally tends to have such a high resistance that if you just plug it into a circuit without a microcontroller, sometimes it can be difficult to see changes with any type of output, like an LED. So usually it's better to incorporate E-Tex into a project that uses a microcontroller. And then this is how you would hook up a stretch sensor using yarn. Again, it's like a very simple diagram. And next is accelerometer. So these are two examples that were created by and conceived of by Mika Satomi of Kobakan. So basically the idea is very similar to a stretch sensor. You basically just have a stretch sensor in between a weighted material, and then that's connected to the other end. So when you sort of throw it or swing it around, that weighted side will pull and stretch the conductive yarn, so you'll get a change in resistance. So you can sort of see her diagram here. And you can also, you don't necessarily have to crochet, you can make this in other ways, which I would encourage. Because a lot of the, creating sensors and switches is sort of, originally it started the thinking was, how can we create components that are already in existence using these materials? So basically, how do we turn hard components, hard sensors, and hard switches into soft things, soft components? And since, many people have started experimenting with these materials, we've also begun thinking about what are totally different ways that we can conceive of what a sensor is or how it's made or how we can read data based on the properties of the material. So, don't necessarily feel constricted by these just because these are the examples that we're showing. Okay, so I will stop again for any questions.
If we're going to make a pressure sensor without any microcontroller for this exercise, is it better to use Velostat or Ionex?
Without a microcontroller, better to use Velostat. Yep, because the resistance of the E-Tex is so high that no electrons will actually be able to make it through no electrons will be able to make it through the E-Tex in order to reach the LED or reach back into the power supply.
Thank you.
Any other questions? All right, now we're going to move in to programming and microcontrollers. So this is very, very basic. I'll say before I move into this, just because the whole programming side of things can be a little scary for some folks. But all of these are very simple, simple code snippets that you can use and change, no problem. So let's start going. So microcontrollers. When we talk about, the objects and tools that we use to program our world, also known as computers, computers are designed to do different things. So we have various computers now that we use every day. We have our phones, we have our laptops, and then we have these huge servers, right? And so they all serve different functions in our lives, and as a result, they've been designed in that particular way. So we also, over the last 30 years, have seen this rise in microcontrollers, specifically open source microcontrollers, which should be a term familiar to you, I believe, after Zoe's talk. So open source microcontrollers that people can, that they don't have to use once. Back in the day, there were microcontrollers that you could only program with one program and it would be seared into that memory forever. You could never use it again. Now we have things like Arduino and Raspberry Pi where we can reprogram them over and over again based on the behaviors that we want them to perform and the data that we want to read. So we're going to specifically talk about the Arduino here and the many different Arduino permutations, I guess. So when we think about a microcontroller, one of the things that microcontrollers are super good at that, for example, a laptop or a smartphone is not so good at is taking information. Well, I guess smartphones are actually pretty good at this as well, but taking information from the physical world, like sensors, doing something to that information or processing it in some sort of way, and then putting it out back into the real world using different actuators like LEDs or motors or speakers. And then that output usually will feed back into the input, which gets processed again. So you can sort of see this loop that happens. But basically, we're talking about input, processing, and output. So we've already talked about the input side of things. We've talked about the switches. We've talked about, creating the switches and the sensors out of those materials. And now for the rest of the presentation, we'll talk about processing. And then in the next class, we'll talk about output. So Arduino, as I mentioned before, is the platform that we'll be working with. It's, as I said, it's open source hardware and software. And it is both a hardware platform and a software platform. So what I just showed you, this Arduino, is the Uno. It's sort of, the most basic version of Arduino. And I always would encourage you, despite all of the different variations of boards, I would encourage you to always start here. Always start on the Uno and then work out to other boards if you want. In 2006, a woman named Leah Beakley who had been working with E-Textiles for a while, she wanted to see a board that was designed specifically for wearables. So she started prototyping that board, and here you can sort of see the journey. She started with the AT Tiny, and then started with that was embedded into textiles, I think neoprene, and then stretchy conductive fabric, and then iterated until she began working with SparkFun, that they picked it up in 2007 and turned it into this sort of circular form factor that had sewable pins, so it was much easier to integrate. And also, not only easier to integrate for wearables, but was sort of rebranded, as it were, to make this type of a field more accessible to specifically women and girls as a way to get them into engineering. And then it's been picked up by all sorts of communities. Here are a few different types of boards that have been designed for wearables. Again, these boards, it really depends on what your goals are and what you want to do, sort of what your proclivities are. There's, lily pad boards, and then like in 2009, I believe, Adafruit came out with the Flora. It may have been 2012, but I'm pretty sure 2009, Adafruit came out with the Flora. I really like the Flora board just because it has a lot of different grounds all over the place that you can access, whereas a lily pad only has one. And then there's also smaller, cheaper boards like the Adafruit Gemma. Again, it just depends on what your project is. Okay, so first we wanted to talk about how we can actually connect to the board and talk to the board, and the way that we do that is through pins. So you'll notice on the Uno there are lots of numbers along the top and the bottom and these little holes. So those are called pins. And a pin is how an input like a button and an output like an LED communicate with the hardware that's actually on the Arduino. So that's how we read information and then output information. And different pins do different things. So there are pin 1 and pin 0 are the serial pins. We're not really going to talk about that today, but it's good to know. So they can transmit and receive data from sometimes from sensors, from other boards. I recommend that if you don't need to use those pins, maybe avoid them because they can cause problems that could be hard to debug, especially if you're sort of just getting started with Arduino. Next, the gray arrows show you where your ground pins are, and the red arrows show you where your power pins are. So in a circuit, when you're working with Arduino or any other microcontroller, you're always going to need to connect to power and ground at some point. Now, this Arduino has a 3.3 volt power pin and a 5 volt power pin. So depending on your circuit, usually you'll probably just use 5 volts, but if you're working with a sensor that only takes 3 volts, then you may need to use that pin. Okay, next, so we've gone through our power and ground pins. Now we're going to go through our input pins and output pins. So all along the top, that's sort of squared in yellow, are the digital input output pins. So if you have a switch that you want to read information from, use these pins. If you have an output that you just want to turn on or off, use these pins. If you have an output that you want to sort of have a range of values, so if you want to fade an LED, for example, there are special pins that you need to use. Those are the pins that have that little tilde, that squiggle in front of them. Those are called pulse width modulation pins, and those will allow you to get a range of output values. So if you want to play many different tones on a speaker, if you want a motor to sort of rotate around as opposed to sort of a jerky motion, and again fading an LED, these are the pins that you need to use, and not all pins have this functionality. Next are the analog input pins. So if you want to read a range of input from a sensor, so like the stretch sensor, for example, you would need to connect into these pins. You won't be able to read that full range if you connect to just digital pins. So now we'll start in on the programming side of things. So first is just a hello world sketch. And again, I'm going to run through these sketches and just give you the basic overview. But once you actually start testing, build the circuit, test the code, it'll make a lot more sense. So when you download the Arduino software and open up the IDE or the integrated development environment, this is most likely what you'll see, unless Arduino has made any changes to their software. So first you will see the toolbar, which is that dark sort of teal, which has sort of like a button for compiling your sketch, just to check it, an upload button. That's mainly, and also importantly, this little guy over here, the magnifying glass. When you press that, will open up what's called a serial monitor. That's where you can read data that's coming in. We'll talk more about that in a second. Next is the text editor. So all of this white space is your text editor. That's where you actually type in your program. And then below that, where it says invalid library in black, that is your message pane. So if Arduino needs to send you a message, that's where you'll be able to see it. And then also it's worth noting at the very bottom here in the dark teal, that tells you what board you're using and what port you've selected that board is communicating through. This will become important in a little bit. It'll help you debug later on. So it's important to remember sort of as with any, when you're doing most types of programming, especially text-based programming, you're going to have your program read from top to bottom, or the Arduino IDE reads from top to bottom. So we have two main parts. So we have the setup, which is right here. Setup, anything that you put in setup only happens one time. And then we have the loop. Anything that you put in the loop happens forever until you tell it to stop. And then when we have any variables, like the LED up here, we want to put those above the setup. Those are global variables. So it means if we want to use the LED variable in setup or in loop, we can use them both places. So we want to keep everything up there for right now. So this is a blinking sketch. So basically we say, all right, I'm going to declare an LED, declare and initialize it. I'm going to say this LED lives on pin 13. And then I'm going to say that this LED is an output by using the pin mode function. And then I am going to write that LED high. I'm going to use the digital write function to turn that LED on. And then I'm going to delay it. So I'm going to turn it off for 1,000 milliseconds or 1 second. And then I'm going to turn that LED back. I'm going to turn that LED off by writing it low. And then I'm going to delay. So what eventually this translates to in the real world is blinking. So it turns on for 1,000 milliseconds or a second, and then it turns off. On, off, on, off. So I'm just going to run through briefly what it would look like if you were doing this on your own right now. So the first thing that you want to do is take your Arduino and plug your Arduino into your computer and open the IDE. Okay, and so when you open it, this is likely what you'll see. So the next thing that you would want to do is tap all of the amazing example sketches that just come preset or come already installed with the Arduino software. So you would go into Basics and then into Blink. So go into, File, Examples, Basic, and Blink. And then that'll open the sketch on your computer. Next, and this part is really important, especially if you start working with multiple boards, you always need to tell Arduino what board you're using and what port you're using. So you go into Tools, Board, and then choose the Arduino Uno. Next, you go back into Tools and you tell Arduino which serial port you're working with. And it'll usually be /dev/tty.usb or /cu.usb. It won't be Bluetooth or anything like that. Okay. Next, you want to upload the sketch, so press that button in the main toolbar. And if everything goes well, then you'll see your LED blinking. I should say, to plug your LED in, you want to have your long leg of your LED going into pin 13 and your short leg going into ground. So I'm going to go back quickly because I don't think I have a slide here. So your long leg would go into this pin 13 and your short leg would go into ground. Now, big caveat, pin 13 is the only place you can do that. It's the only time that you should stick an LED directly into your board because it has a resistor on it. So all pins output 5 volts if you turn them on. And we know that an LED takes 3 volts at most. So we have an extra 2 volts that we need to use. And if we don't use it, it puts a lot of stress on our LED. So we don't want to plug LEDs directly into our board. But pin 13 has a resistor on the Arduino that allows us to do that without causing damage to the LED. And going back. So we already talked through the different functions. So we can use digital write to write a value, to write high or low to a pin. So to write 5 volts to it or 0 volts to it. Now, the next sketch that we want to talk through is basically how we use a serial monitor. Here we are just basically turning an LED on or off, right? But there are other ways that we can use our Arduino to communicate with our computer. And this is especially helpful, for example, if you want to see what values you're getting out of your sensors. So we use what's called the serial monitor. So you just press that little button on the toolbar. And we use two functions here. One is the serial.begin, and that goes in setup. And the other one is the serial.println. So once you upload that, if you upload that to your Arduino, this is what you'll see. So this basically says, basically has the Arduino printing the words "Hello World" into the serial monitor. So again, it's helpful for reading sensor values and debugging. Just as a quick example, so a quick explanation of why you see this serial begin 9600. This is the standard number that we use when we want to communicate between the Arduino and the computer. You may see it change if you decide to use some types of sensors, but generally it'll always be that. And this is called the baud rate. And this basically establishes the rate of exchange between the Arduino and the computer, so one isn't sort of talking over the other. All right, so now we're going to move on. Now that we've sort of taken a little bit of a dive into the programming environment, we're going to talk through some of the components and tools that we'll need to use to build circuits that can integrate with the Arduino. So the first that you have heard me mention a couple of times at this point is a breadboard. So a breadboard, if you've never used one before, it's like can be highly confusing and to sort of wrap your head around how it works. But once you use it frequently, it's one of your best friends. This is what we use to prototype a circuit. So there are, in a sort of standard breadboard, what you see is the white breadboard in the middle. All of these horizontal lines, so A, B, C, D, E, all of those are connected. Okay, so any component that you put in line 1, there's like a metal strip going underneath of it that allows those to be connected. But line 1 and line 2 are not connected; those are separate. Now the vertical lines that have the power and the ground, those are all connected going vertically. Those are our power and ground buses. It makes it a little bit easier for us if we will probably need to make a lot of ground connections in the circuits that we build. So it's much easier to access those ground connections at many different points through this sort of bus line. Here are some other examples and variations of breadboards, right? It's just a tool that we use for prototyping. Some people have created softer versions of those that are helpful to them. Another component that we'll be using that's helpful for prototyping is just wire. So we can use solid core wire or stranded wire. When we're talking about prototyping in breadboards, we want to use solid core, and usually 22 gauge is what we use for a breadboard. And if you just want to keep it really simple, you can use jumper wires. As you can see right here, this sort of like pile of them with the black ends that are sort of plug and play. The only thing to note is that sometimes they can become disconnected at the end. So if you have debugged or tried to find the mistake in different parts of your circuit and you just don't know what else to do, try exchanging a jumper wire because sometimes they can break. The next component is our resistors. So resistors, as I said before, they limit the amount of electricity that can flow through a certain point. So we talked about resistive fabrics, yarns, and threads. This is basically sort of like the component, much more standardized version of that. And resistors can come in many different values. For example, you'll see the 10K ohm resistor used very frequently, and you'll be using it pretty frequently, along with the 220 ohm resistor. So they come in different values, and they also come in different wattages. So you can see there's like a really tiny one all the way to the right, and then a really big one all the way to the left. And we'll mainly use quarter watt resistors. So now we'll get into some circuits and code. So there are two main circuits that we'll be talking about today, and a couple of different code examples. And I always like to start this by saying you don't have to know a ton of code to do cool stuff, especially because we're working with such fun materials. You can do a lot of things with some really basic code. So first we're going to talk about the circuit for, I'm going to move this down here, the circuit for a switch. So as you can see here, we have a switch, and then we have our LED. We have a resistor that connects our switch to ground. And then in between the switch and that resistor, we have that green wire that's connecting to our pin on the Arduino. And that is a really, really special sort of configuration that's called a pull-down resistor. So this is an example, or one example of where you actually, never mind, this is not what I meant to say. It comes next when we talk about a different type of circuit. Anyway, this is the pull-down resistor. So this basically makes sure that Arduino doesn't get too much noise. It makes sure that if the switch is in a high or low state, that it's actually there. If you didn't have this resistor, the button would be bouncing all over the place, and you get a lot of values that are not helpful. And so we use, again, a 10K resistor with this circuit. And then on the other side of that switch, we have it just going straight into power. And then we have an LED. We have that LED connected to a 220 ohm resistor to make sure we don't damage it. And then we have the other side of that LED, the power side, going to a pin. So then here you can just use like a basic example from Arduino, the button example. And then we have our button pin is pin 2, pin 13 for the LED pin. I wanted to highlight that a constant int variable is a variable that doesn't change, and then just an int is a variable that will change. Sometimes it can get confusing. And so here we use a function called digital read to actually read the input, the information that's coming in through the button. So we digital read the button pin, and then we store that in a variable called button state, and then we use a basic if statement. So we use a conditional, and we say, okay, if that button state is high, so if it's pressed, let's turn the LED on, and then if it's not pressed, turn it off. So that allows us to determine if it's been turned on or off. You can also, there are also what are called internal pull-up resistors that you can activate. I'm not going to go into that here because I think it's important just to actually use the components first. But if you find yourself in a situation where you don't have a 10K resistor, or you just really don't want to create the space for that in your circuit, try using an internal pull-up resistor instead of using that, that physical component. So I mentioned using an if statement. So this is basically an operator that you'll find it's pretty universal in programming languages, and it's used to test a condition. So we say, you know, if this condition has been reached, then do something else. There are many different ways that you can write it in Arduino, as I've laid out on the right side of your screen. If you want to test, or if you want to have different statements together, you can use if else, and you can basically have like unending if statements. So you can say, if the value rises above 500, do this. Else, if it rises above, 1,000, do this. Or if it's in a certain range. So you can add these statements together to create a set of controls, for your program. So next on to, so this is what I was mentioning. You can use input pull up if you don't want to have, if you don't want to use a physical component for your input resistors. So we're not going to dive too deeply into that. the main thing to note is that if you do use this, the logic of the LEDs changes. So if you say, all right, if the switch is basically, if you have a button that's pressed, when you put low, the LED will actually go on. Like the logic is inverted. So if you use the internal pull-up resistors, just know that if you want, for example, an LED to turn on, instead of using high, then you're going to use low. I know it's a little confusing, but that's just sort of the way that they've done it on the Arduino. So next, we're going to move on to the sensor circuit, which you'll probably see looks really, really similar to the switch circuit. There's just one sort of really big difference. Instead of calling this a pull, so this is not a pull-up resistor, even though it looks like it. This is what's called a voltage divider, and this is a really big, sort of can be difficult to wrap your head around at first, but it's a really important concept to understand if you're going to be working with handcrafted sensors. So basically, this is what I was going to say, going back to this question of when do you use components in series. This is an example of when you would use two components in a series. So here we have a 10K resistor that is then, we put a wire going from our analog input pin to the Arduino in between that a resistor with that stable value, that 10K, and then a resistor that has a varying resistance. And we use that stable resistor basically to compare the value of that, that variable resistor. And then we just have our basic LED. Oh, I should mention though that LED is going to pulse with it's going to a PWM pin, pulse width modulation pin, because what we're going to try to do is say, as we're stretching that sensor, we want to map, or we want, when we stretch it, we want that LED to get brighter. And then when we release it, we want it to get dimmer. So we have to use one of those special pins we talked about before. So voltage dividers, just to go a little bit deeper into that. So when as we mentioned before, these sensors are all about manipulating changes in resistance and creating the opportunities for that. But the Arduino is completely digital. It only reads things in binary. It only reads on and off. Also, it cannot read changes in resistance. It can only read changes in voltage. So we basically need to create a circuit that will allow us to read a change in resistance as a change in voltage. And this is what a voltage divider does. So when we divide the voltage, we can divide the voltage by using two resistors. So if we have a circuit, as you'll see in the top diagram, that's 5 volts, if we put two 100 ohm resistors in series and then divide them in the middle, we know that we have 2.5 volts there. And we can also do that, we can sort of like vary that a bit and just read different voltages, and that's something the Arduino can work with. And there are a lot more tutorials on this from SparkFun and CovaCon and other places. Okay, so next you'll see the analog input program. Oh, I think somebody's maybe turned their mic, turn their audio on. Mute. Okay, cool. So next, the sensor, the analog input sketch, it's very similar to the switch sketch that we just saw. The only difference is a function, instead of using digital read, we use analog read, as you can see right here. So we sort of do the same thing. We say, let's read that analog, the sensor pin, and then store it in a value. And then we're going to print that value, see what it is. And then based on that, we're going to write that value to the LED using the analog write function. So this particular sketch is not in the examples, but it is in the set of examples that I'm going to, it's not in the Arduino examples, but it is in the examples that I'm going to give you. So sometimes the the data that we'll get from a very simple sketch like I just showed you is not, we can't really do a lot with it because, you know, the values are all over the place, or maybe they're super high or they're super low and they don't map to the LED quite well. So here are a few techniques that you can use to get more meaningful data. So you can, you know, for example, have that LED mapped perfectly to that stretch sensor. So I'm just going to give sort of a very high level overview of each of these, and then you can try them, test them out on your own, because I want to leave enough time for questions. So first is mapping. So this is a really, really, really helpful function that you can use when you're working with sensors. So basically it says, okay, we're getting this sensor value, and let's say we are getting a range from this sensor that is only between, I don't know, 5 and 10, right? But we actually want a range that's between 0 and 255, because that's the range of the LED, right? We can either turn it all the way off at 0, or we can turn that LED all the way on at 255. But we only have this value from our sensor that's from 5 to 10. So we can actually make that range usable by using the map function. So we basically say, all right, let's program this so 5 actually becomes 0, and then 10 becomes 255. And then so all of the values in between get mapped onto that range. It's really, really helpful. So next, the next technique that you can use is a function called constrain. So this makes sure, and usually you can use this with mapping, this makes sure that the values that you're working with only stay within a particular range of numbers. So sometimes, for example, when you use map, if the values, like if you stretch it really, really far and there's sort of an erroneous value, it can sort of throw off your mapping. But if you use constrain, if you get that crazy outlier, it'll just cut it off, and it won't mess up how it's being mapped. Next is smoothing. So this is an example that you can find in Arduino. This is really helpful because basically what it does is if you have some jumpy readings, it'll take 10 of those readings, or it'll take a subset of those readings. It will average them together, and then that is what it will spit out as the main output value. This can take a little while, or can be a time lag to it, and in Arduino, time lags are in milli and microseconds. But basically, it's helpful to be aware that the higher readings that you're averaging, the longer it may take. But it's really helpful if you have a lot of data that you need to process. Next is calibration. Calibration is helpful if you need to get a certain range. If you have a sensor that you're working with that you basically want to define the minimum and maximum values that you're using without having to sort of like go back and stretch it and see, okay, that's the maximum, and then let it go and say, okay, that's the minimum. This will allow you to do that easily in like the first 5 seconds of when you run the sketch. Okay, I am going to actually hold off on questions until the end and just go through some main takeaways. So I know that was a lot to take in, but hopefully I've provided enough resources that you can sort of dive in where you want to and where you feel is the most helpful. And sort of the main things that I really want you to take away from this as you start working on your assignment for next week, again, are these sort of 3 rules around electricity. So electrons are lazy. Watch out for short circuits. If you feel your circuit getting hot, if you see it smoking, like immediately unplug or take away the power from your circuit. Next, electricity hates waste. So remember, you sort of have to have power, your components, the power that your components need, and the power that your microcontroller or your battery is putting out need to be in line, and that circuits are a system. So orientation matters for some components like LEDs, but not for other components like resistors. So next big takeaway, you can manipulate resistance in 3 ways: through distance, contact, and surface area. Next, always remember that secure connections, you must create them in order for your circuit to work. And this can be one of the biggest challenges when you're working with soft materials. So always be sure to test them with a multimeter using the continuity setting if you have if you think it's a questionable connection. Also on that note, I may have forgotten to mention, like if you're sewing in a component, always be sure to sew around it multiple times. I usually sew it around like three to 5 times, depending on the type of thread, especially if more times if I'm not soldering to it. It's just good to know that you're doing your best to create the securest connections possible. And then lastly, keep your circuits super clean. So you want to tie up any loose threads or secure them with glue to make sure that you avoid any short circuits. So, preventative measures to make sure that your circuit will work are always worth investing more time in, because if you finish putting all this time into constructing your circuit, and then it doesn't work at the end and you have to spend more time debugging it or undoing it or whatever, that's usually a lot more frustrating, at least for me, than just making sure that I try and do it right the first time. Okay, so questions before we give the assignment?
They are all like zombies.
I kind of also feel like a zombie. It was a lot.
Yeah, it was like in one breath. Like, I mean, thank you so much. It was like, woo. So, we will have local tutorials tomorrow in all the labs, and we will go. They will sleep on your presentation. I hope so. So probably if they have more questions, we will be sending you some questions through email and things like that. But at the moment, I don't know, they don't know what to ask.
If you can formulate questions. Sounds good. Okay, well, on that note, I will go ahead and give you your assignment. So your assignment for next week is to create one digital switch and one analog sensor. And then use that to connect that sensor and switch to your microcontroller, get the readings from it and map the values, and then program an LED or mini vibration motor to interact with your sensor, and then integrate it into a swatch using hard and soft connections. So a swatch, just if you have not heard that term before, meaning just like a small sort of piece of fabric. It doesn't have to be a larger project, just an example. Okay, and that is all for this week. And I look forward.
Sorry.
Yeah, go ahead.
Can you go back to the slide with the assignment, please?
Yeah.
What do you mean with mini vibration interaction?
Sorry, that should be mini vibration motor. I'll change that.
Okay.
After we get.
Okay. Thanks.
No problem. All right. Any other questions on the assignment or otherwise? I'll be available by email and we'll try and get back as swiftly as possible.
Sorry.
Tomorrow.
So both the digital and the analog one should be connected to a microcontroller.
Mm-hmm. Yep, so just make one of each and then test them using those 2 different programs. And you'll find link to the code for all of those, so you can just upload it, plug and play. You should really focus more on the construction of the sensor and switch, and then you can just upload the code that I've already provided.
Okay, so the micro. Okay, perfect, thanks.
Yeah. Right, any other questions about the assignment?
I think you can stop sharing the screen. Yeah, perfect.
Great. Oh, yeah. Hang on, let me see if I can jump out of this. Okay, cool.
Yeah, so that was tough. Thank you so much for taking more time, and thank you also for being able to give the class, and congratulations. Liza just became a mother, so I think it was your first moment of not having the baby next to you or something. So
you may have heard.
No, we didn't hear anything.
Okay,
so really, thank you so much. It's always wonderful to get your way of explaining electronics, because for some people it's difficult, and I think that it's very clear. And I also invite everybody to watch this again and again. For me also, I'm watching it many times, and still there are still some things that, it's all about practice in the end.
Yeah.
So yes, for the ones that feel more pro, because we have some people already that they are like Fab Lab managers, and working with the electronic textiles is not like working with circuits. We had a conversation like some days before, I think, where we were saying that if at the moment we are going to PCBs, everything is getting closer and smaller. In electronics textiles, it's like a big drawing, and maybe you have to go open and bigger and bigger. Try to dominate the practice. It's different. You can use the circuitry as a design, so that you can also have it seen obviously, having it your design is the circuit. It's not that you are trying to optimize space, but you are designing and you use the aesthetics of the circuit. You can also do integrated embedded circuits, that everything is closed like a black box, and then it's all finished and you don't see anything. It's a matter of your choice. You can choose either. For the ones that they do not have a lot of conductive materials, you can work with copper tape and vinyl cut it. We have this in the Fab Labs. And make sure that you really pay attention to the hard-soft connections part that Liza was mentioning, because this is the trick, actually, no? So it's how to translate from rigid to soft. So this is for the ones that they feel more pro. Okay.
Cool.
That's
Well,
from
thank
my
y'all so
side.
much.
Thank you so much for taking the time, and see you next week at 9 your time. Yeah.
Cool.
Thank you. Thank you. Bye-bye.
Bye.
Ciao.